What are isotopes? So you are going to go to PhET and you're going to look for isotopes. You can copy this URL, or if you just Google PhET isotopes, it should take you to the right place. Make sure that you press the green plus symbols next to symbol and abundance in nature, and change the scale to read in atomic mass units. So go ahead and take some time to work through questions 1 through 12 in this classwork. And whenever you're ready, come back here to check your work. So question 1 here, we are looking at different isotopes of hydrogen. So we have hydrogen 1, hydrogen 2, and hydrogen 3. Those are all made by adding neutrons. So the number of protons for all of these is going to be the same because these are all hydrogen. They have to have one proton, otherwise it wouldn't be hydrogen. Hydrogen 1 has no neutrons, hydrogen 2 has 1, and hydrogen 3 has 2. So for the symbols here, the number on top, which is your mass number, is going to be different for each of these isotopes. And these are the masses of each isotope. Now it makes sense that the isotope hydrogen 3 is the heaviest because it has the most neutrons. It's got the biggest mass number. And if we look on the periodic table of elements, the mass for hydrogen is given as 1.008. So that's because this is a weighted average. Almost all of the hydrogen in the universe is hydrogen 1. So the mass, the average mass, is going to be closest to the mass of hydrogen. But it's going to be a little bit higher than the mass of hydrogen 1 because we have these little really small fractions of these heavier isotopes. So write a definition for isotope. They're going to be the same element, meaning that they have the same number of protons, the same atomic number, but they have different numbers of neutrons, which means that they have different mass numbers. So hydrogen 1 is much, much more abundant than hydrogen 2 or hydrogen 3. In fact, in the simulation, you probably saw that hydrogen 3 was kind of wiggling around to represent that it's unstable. So in the next section here, we want to select Si from the table of elements. That's going to be silicon. And in the simulation, we have 3 isotopes of silicon. Now we want to use the key on the table of elements to find the atomic mass of Si. So this is the value that's on the periodic table. So what we're going to look at next here is in the simulation, I'm going to put one of each of these. And if you notice, my average here is 28.97573. If I add silicon 30, notice that that mass goes up. And if I add silicon 28, notice that that mass has gone down. So we're trying to match that number from the periodic table to the number here in our simulation. So if I keep increasing silicon 28, this weighs the average closer and closer to the mass of Si28. So this is pretty close. Let's see if we can get a little bit better. That's even closer. So this is what we get for silicon 28. We got 92.1. For 29, we have 5.3%. And for 30, we have 2.6%. So this is what we got. And what you need to understand is that one type of silicone is much, much more abundant than the other 2 isotopes. So the average is weighted towards the mass of that most abundant isotope. So if we compare this to what it is in nature we've got 92, 4.6, and 3.0. But we still see that silicon 28 has to be the most abundant isotope in order for us to have the correct average molar mass, molar weight. So when we add the silicon 30, we saw the average rise, and when we added silicon 28, we saw the average fall. So this is what we just saw in the simulation here. Your numbers might be slightly different from mine, but based on this evidence that we've just collected, we would dispute this statement. Each isotope has a different percent abundance for each element. So if I were to reach my hand into, a bucket of 100 silicon atoms, I'm most likely to pull out a silicon 28, much, much less likely to pull out a 29 or a 30. Okay, so in this next question, we want to actually calculate the average atomic mass of magnesium. So in the problem, you can see that we have 3 different isotopes, and I'm just going to call that A, B, and C. So I've filled in this data from the problem. Now what I want to do is find what we call a weighted average. So essentially, I need to figure out what 78.99% of 23.99 is. I need to figure out what 10% of 24.99 and what 11.01% of 25.98 is. So what I want to do first is convert this percent into a decimal. And so if you want to convert a decimal into a percent, you would multiply by 100. Here we're going in the opposite direction. We want to take a percent and change it into a decimal. So we're going to divide by 100. Now that we've done that, we're going to take our decimal and multiply that by the atomic mass of each isotope. So once we get these numbers here, notice that this 18.949 is the biggest number because isotope A is the most abundant isotope. So the last thing that we would need to do here would be to add these all together and get our answer. And we can always look at the periodic table to determine if our answer is correct, if you know what element it is. So if you look up magnesium, the value that we get on the periodic table is very, very close to this value, so we know that we did it right. The next couple of questions, I'd like you to go ahead and try on your own and then return here whenever you're ready to check your work. So the element copper has naturally occurring isotopes. Copper 63 has an abundance of 69.2% and a mass of 62.93 AMU. Copper 65 has a relative abundance of 30.8% and a mass of 64.93 AMU. So we want to calculate the average atomic mass of copper. So we have 2 isotopes here. So what I want to do here is figure out what is 69.2% of 62.93 and what is 30.8% of 64.93. So for copper 63, I'm going to multiply the mass of the isotope times the percent abundance over 100. And then I'm going to do the exact same calculation, but with my values for copper 65. So now I need to take these 2 numbers then and add them together to get my final answer. And we can check this matches what we see on the periodic table, so we know that we did this right. Now notice that the mass is much closer to 62.93 than it is to 64.93. And that's because the 62.93 isotope is much more abundant than the other isotope. So that skews the average towards that more abundant isotope. There are 2 naturally occurring isotopes of gallium. Without doing any calculations, look at the periodic table and determine which isotope of gallium has a higher natural abundance. So if we look at the mass of gallium 69, it's 68.93, and gallium-71 is 70.92. So there's only 2 isotopes. So if these isotopes were equally abundant, then the average would just be right in the middle of these 2 numbers on the number line. The average mass of gallium is 69.72, which is a little closer to the mass that we have for gallium-69 than it is to gallium-67. So this is a difference of 0.79, and this is a difference of 1.2. So because my average is slightly skewed towards gallium-69, that must be the more abundant isotope. At the end of this classwork, you have your next journal write. So write a procedure for how to find the weighted average used to calculate your grade. So assessments are weighted to 50%, classwork is weighted to 30%, homework and the quarterly assessment are 10 and 10% each. So let's say that this student had, an average score of 70 in their assessment category, an average score of 80 in classwork, and 100% on homework, and a 70 on quarterly assessment. So we could use those numbers and calculate what their weighted grade is.